So, I'm going to talk about how we solve engineering problems using Python. We have a big problem with the seismic superficial Rayleigh wave analysis, and we have a lot of data when we design new or we upgrade train lines. So we use Python to solve this problem. So why am I talking to you about this? A little bit about myself. I'm a civil engineer, and I have another master's in geotechnical engineering. Geotechnical engineering is the science of soil, pretty much. It involves geology and engineering, and it can get as numerical as you like or not. I have a few pet peeves. I name only two, because it's the first time I meet you, so I try to be nice. Everything should have units, and I'm a very strong advocate of units. And the output should be in a pre-agreed format. And I can't stress enough the second point that if you agreed with the client from the beginning, then it will solve a lot of problems. A little bit of introduction about the seismic waves. What do they do? We have the pressure or primary waves, which are the P waves, and the secondary waves or shear waves. You can see them at the left of the picture. These are the waves that arrive first when an earthquake happens. Then we have the surface waves, love waves, and Rayleigh waves. They arrive last, but they tend to have the biggest impact, as you can see on the slide here. This is from Berkeley, and it's the seismograph output, and you can see that the Rayleigh waves have a very high amplitude. When the train moves, therefore, the Rayleigh wave moves with the train. A similar effect to the sonic boom is the ground vibration boom. The train moves faster than the surface Rayleigh waves, and therefore the soil fails, and this can cause serious damage to the tracks, even brittle failure. So the train has to be, the Rayleigh wave has to be faster than the train all the time. So how do we fix that problem? Practically speaking, we can reduce the speed of the train. But this will not be, you don't want to take a lot of time to go home, right? You want to go home fast. So another way is to engineer the stratum, the substratum of the track, and implement stiff layers. I added a GIF there to show how the Rayleigh wave works, because I tried to explain it with words and I failed dramatically. So if you watched my talk at PyCon UK last year, it was similar to that. This is basically part 2, Rayleigh waves with revenge. So it came back to haunt me. The initial problem was that we have a lot of data, and geotechnical engineering is not, the procedures that we have in place are not designed to deal with a lot of heavy data, a lot of numbers. Some of them don't make sense at all. It's like, why are you here at first place? So we have small or medium-sized projects, 10 boreholes, Excel spreadsheet. It does the job. Everyone understands it. Everyone can do it. Now we have a big project. We have 1,000 of boreholes. We have a lot of data. We want to analyze this data. We want to export this data on a map, and Excel is slow. And this is a portrait of an engineer when they saw this problem. I'm joking. It's not. I got it from the internet. So the problem got a little bit more difficult for me because the data format changed. Also, I think that this one is missing units. So guess who wasn't very happy when saw that? So the 3 letters that are not included in the presentation because it's confidential data for the client are stratum identification. So it could be clay, it could be sandstone, it could be sand. I don't care about the description of the soil with my problem at the moment. I will care later when I try to do a comparative analysis. Like they will say, for example, clay has this amount of this SPT values, which correlates to that stiffness. Is this correct? So it's good that I don't have it because I can do a lot of blind tests. What I do have is the thickness. And then I correlate this thickness with shear wave velocity. And I find the shear wave velocity, and then I do my calculations to find the Rayleigh waves. That was last week. In the past, I had semi-structured data, everything was nice, and, you know, it came in small amounts of spreadsheets, but now it comes in large CSV files. And on top of that, a criterion has been implemented. So after I describe the main model, I will tell you the part 2 of the story. So we're using the Lyon and Aung, if I pronounce it correctly, model, which takes the equation from Viktorov to calculate the Rayleigh wave velocity using the Poisson's ratio equation, and then it adds a weighted factor on top of that. So it's a single integral, which is fine because you can do that with NumPy. You can calculate single integrals with NumPy. However, NumPy hasn't got a Neville solver, so we chose Lyon and Aung instead of the Duncan model. I'm trying to write a Neville solver for NumPy, but bear with me. I'm really trying, and I struggle with C a little bit, so if you have any advice how to put a new module into NumPy, please come and see me at the break. This is the three-dimensional model of the train and how it propagates. So we have the ballast, which is engineered control field. We know the properties of it, layer 1, layer 2. So this stage, the layers do not correspond to different geological formations. So we do not have layer 1 comprising glacial till, layer 2 comprising Mercia mudstone. It can be the same geological formation with different properties. Okay? So for the geologist in the room, anyone? Okay. So I used this model and I started replacing weak in situ material. Weak is a term used loosely here, material that doesn't fit the criteria of the Rayleigh wave velocity we want. I started replacing it with more competent strata, and by competent strata, I mean material that can actually take Rayleigh wave velocity greater than 160 meters per second, or at the time it was 100, I think. And I found out that when I increase the thickness of the competent material, as you can see, I can increase the Rayleigh wave velocity, so happy days, the train can go faster. And I wrote code about it. And I was very happy about it because it solved all my problems for now, for the time being. So I used the least squares and linear interpolation to find velocity per hertz, and I was very happy. And then I found the outliers. And I was happy, but I had to explain this to another engineer saying there's something wrong. I don't know what's wrong. We have to look at it. Here we have a very stiff material at the top, and then a very weak material just below, 1 meter below. And this is where you have to look at your data and say, I don't reach a minimum at any time soon. What's going on? And this is very good that it happened at this time because we could send it back to the person that sent us the data and say, are you sure it was there? Could you please do more site investigation before you build anything? It saves money. So we were happy. And then we get no data. We have one value, which, again, it might be the case, it might not, but you'd better ask, right? So the replacement criterion that I had to implement. I was told to replace the in situ material with competent material so that the Rayleigh wave velocity for a frequency between 5 to 50 hertz is greater than 160 meters per second, which is okay. I mean, it's a simple sentence to translate into an algorithm and implement to NumPy. Problems. Here's an example that I made up. The initial stratum thickness and shear velocities are the following: 3.56, 9.71, and 1,000 meters. That's the half layer. And I deliberately chose very small shear wave velocity. The shear wave velocity correlates to the Rayleigh wave analysis, so it's fed in the model. And then I started saying that I will run a loop, and I will find where the minimum Rayleigh wave velocity is greater than 160, and then I will stop. So that's the replacement criterion too, where I replace the top meter with stiff material. But then I said to myself, what happens later? What happens after 1.5 meters? What if I keep digging? And I found something quite interesting, that after 2 meters, I think, yes, 2 meters, no matter how much material I replace, the minimum velocity is the same, which was something that I don't know if I was expecting it. I was just curious to see what's next. So I ran it to the very end. And then I decided to represent it graphically. May I remind you at this stage that the frequencies that I had to look in between was 5 and 50 hertz. However, I said, what will happen if I exceed 50 hertz? What's there? Do I have an asymptotic on the x-axis? What happens with the graph? With all those questions in mind, I present you replacement scenario 1, where we reach a minimum Rayleigh wave velocity at about 50 hertz, which is okay, but it's not the minimum we want. We want something more than 160 meters per second. Then we want scenario 2, competent material. Then you see that we reach a minimum after 50 hertz. So this is something that I wanted to communicate to my client and say, after 50 hertz, we have a minimum. Do you want to take a minimum between 5 and 50, or you want to acknowledge something that's greater than 50? How will this affect your design, your end of story, because I don't know what happens. Same happens with scenario 3. And scenario 4, we started seeing the asymptotic. Keep replacing, we have a similar pattern. The minimum moves further to the right until you reach really high replacement depths at around 7.5 meters and less, and higher, sorry. So when you're from 7.5 meters onwards, it starts to show a behavior like that the minimum moves towards the 0 on the x-axis, and the value remains the same. So the conclusions are here. A, make sure that you know what you're typing in, because I had a lot of problems with data that wasn't fit for purpose. Manipulate your data to the nth degree that it's legible from the software that you write. Make sure that you know that you might need to examine further than 50 hertz. And always communicate with the client and make it a module, because at the end of the day, my client will come and ask for it. Whichever company does repair works for Rails, they can come and say, give me the modules you wrote. And I can prove that I actually did science with their data, which is always nice. So that's all from me. Thank you.
Thank you, Dani. Plenty of time for questions. Yes, over there.
Curious, I don't know if this is making any difference. Does the sort of complex nature of the novice and that of the soil have any influence? So in terms of thixotropy, so if you does it make any difference how the velocity of the trade is achieved? You know, sort of effects like with cornflower, for instance. Does it help if you get that? You know, if you either accelerate really gently or really slowly?
Yes, you're talking. Yes. Sorry.
Repeat the question for the recording, please. Repeat the question for the recording.
Or paraphrase the question.
Oh, okay, sorry. So if I got it right, the question was comparing the soil to a Newtonian fluid and asking on the horizontal, on the x-axis, how the density or the viscosity, or I would say the anisotropy of the soil affects the propagation.
Is the thixotropy as well?
The thixotropy, yeah. Soil does not. The materials that I'm looking at do not behave like non-Newtonian fluids, so I'm good at that. However, we assume that we have borehole data, so it's point data. We don't have continuous data. So if we assume that we have continuous data, we might have to look at finite element analysis or something more detailed. So this is a little bit more generalized data. I understand your point, and it happens. I can tell you that if you have a lens of material, if you have a lens of organic soil, and I saw that happen on sites, okay, it massively affects what you're doing underneath or on top. However, they generally proceed with other types of testing, which is non-intrusive. People on site do sonars to find cavities and very big differences in soil density, with what's it called, with an ultrasound and things like that, if I can explain it properly. So, or a ground penetration radar. So there are methods to find if there's something wrong. However, we can't have an intrusive site investigation every, let's say, 2 meters. It's not financially viable. And also, all these parameters are weighted and factored. So it's a very conservative model. So it takes into consideration that if something wrong happens, we will have enough time to detect and repair.
Thank you, spot the ex-material scientist.
Any other question? I have one. If not, yeah, go ahead.
For the more lay people in the audience, could you just explain in situ and competent material? What do those words mean?
In situ material is what you find on site.
Right.
So,
What's there?
yes, what's there already. So, if you go up in the mountain for a walk and you go up on a slope and start digging, you'll remove the made ground or whatever is laid, and then you will find some rocky material or some sandy material. That's the in situ material. It means on site in Latin, and that's the only Latin I know, so don't ask me for anything else, okay? Just to be clear, Emmanuel. And competent material, in this case, it means that it's a material that does the job for us. So that's it.
Okay.
That fits the criterion pretty
So
much.
your whole calculation is how much of the on-site do we need to replace with what we
Yes.
know is control and we like it
Exactly.
in order to achieve a certain
Yes.
effect, so to speak.
But sometimes we don't have to replace anything on site, and that makes people very happy. So just to give like a happy note here.
So the graphs you were showing at the end, I think they were single-site models,
Mm-hmm.
and you talked at the beginning about having up to 1,000 boreholes measuring results. How do you measure the error between your idealized models and the 1,000 different borehole readings you have? Is there a connection between them?
This data, the data that I'm using, the parameters that I'm using for the soil analysis comes from the in situ testing, like the boreholes we described before. So this is the output of the looping. Now, I run this. Imagine that you have 1,000 boreholes and you have to do this test for every borehole. It takes a while. This is why I stop the measuring at when they meet the criterion. Now, as I said before, I don't have any information to test this data. What happens is that people do site investigation and we can correlate my curves to theirs if need be, but I don't have this at the moment, so I don't know. That will be part 3. So, yeah.
My question is, these graphs, they look very smooth. Is that like, have you not collected a lot of data? Like, because normally, you don't see, there are always errors in data, right?
Yes, but this does not depict data. It's
Repeat the question.
oh, sorry. Sorry. The question was that the graphs here, and let me show them again, look really smooth. And the question is, how did I collect the data to make the graphs look so smooth? Because usually you don't get that. These graphs are the output of these calculations, which use the data. We use the Poisson's ratio, that's the ni, the error nu, depending how you interpret the Greek alphabet. And the W parameter is a weighted factor. So the curve is smooth because you run integrals on depths and velocities. So even if you have one outlier, like here, the curve will still look smooth because you are integrating under parameters. So you're not looking at the outlier as what's this point outside the graph. You're looking at the behavior of the graph, at the f dash x. Okay.
Thank you.
Any other question? I'll have one then. The work that you mentioned on NumPy, and you're looking for some support. Can you tell us more about that? What it is you're doing, and more importantly, could a non-expert in your field help you out?
Yes, please. Anyone that can help me write a Neville solver for differential equations for NumPy, or show me how NumPy works, because I tried to download it and start typing something in for submission, and at the moment I fail massively. So it's a Neville solver is a way basically to solve a differential equation, and I'm trying to just add it in for reviewing, and that will be my contribution to NumPy, and will enable me as well to do another model, another seismic model, use the Dunkin model to compare the two methods, the Leong-Kaung and the Dunkin model, and see what exactly goes on. So it is for my own use, but at the same time it's something that's missing, and I'm trying to write it. So
Excellent.
that's all.
Any other question? Well, if you have more questions, you can have a chat with Dani during the break. Will you be around later for a drink?
I
Maybe
have to catch a train.
half a drink before
Half
a
a
train?
drink.
Well,
Two quick sips.
okay, so during the break, let's thank Dani again.
Thank you.